Hey everybody, thanks for joining today, and huge thanks to Lefteris for joining us today to present Pilotfish. Lefteris is a professor at IST Austria and a researcher at Ava Labs. So thanks so much for joining us.
Thank you very much. Yeah, so this talk I have made a bit more generic on elastic scaling Web3. The last part is Pilotfish, but I really want to discuss all the layers. So first of all, thank you very much for having me. As you said, I'm Lefteris. And let's start. What is elastic scaling? Elastic scaling basically is the ability of a system to dynamically adjust its resource usage based on the workload demands, right? So if we get to some example here, we have Alice, and Alice is playing a video game on the cloud. And this cloud is actually elastically scalable. What does this mean? This means that when Alice later goes to school and tells all her friends about the school games that she is playing, then we're going to see that we're going to have a very nice resource usage. For example, Alice takes her friend and they skip the last part of school actually in order to go to play the game. The cloud already manages to have two users without any problem, but later on in the afternoon, when Bob and Nick also show up and they won't play the game, if they try to play on the same cloud server, then we're going to have some issues. On the one hand, the cloud could allow everyone to play with the existing resources, but this is going to probably have really bad user experience because they cannot really support the full game experience in one cloud server, or it will reject the users. But if your cloud is elastically scalable, then it can spin up new resources, which will accommodate the new users, and everyone is going to have a nice user experience and the ability to participate in any kind of game. But if later on Alice is the only one that stays up to play the games, is the real gamer here, then we don't need all those resources, so we can very quickly spin down the CPU, the memory, the servers that we need for the 4 users, so that we don't pay the price of being ready to have more than 2 users when we don't actually have them. So what are the key components of elastic scaling? Firstly, we care about auto-scaling. We want to automatically adjust the number of compute resources based on the workload demands. And secondly, we care about load balancing. This means that we want to distribute the incoming traffic across multiple instances so that there is an optimal resource utilization. This is what we want to do with elastic scaling. But why do we want to have elastic scaling? Well, firstly, because it gives us cost efficiency. We only pay for the resources used. We don't have idle capacity waiting to be used in case there is a surge, a spike of the workload. And also we get good performance. We can maintain consistent performance even when we have peak and on off-peak periods. And as a result, the users are not going to get bad user experience because there is a lot of them at peak times. Now, what's the state in Web3? Well, we don't really have elastic scaling. For example, in popular blockchains such as Solana, we have some very high minimum validator requirements, and this is in order to be able to accommodate spikes of usage. The problem there is that if there is very low load, then because of there is this very high validator requirements, the validators basically cannot even break even. So we either have to increase the fees, inflate the currency to give them more fees, or the validators are going to go bankrupt. So not really good. And even worse, and we've seen in the latest days, where the load is too high, on the one hand, the fees and the costs are no longer linked. This means that we no longer have a market where users pay fair value for the resources. It's an auction. We're really now running an auction, and users have to pay a premium to participate, or they have to go away. There's no longer a service. And even there, if we cannot really accommodate the load and there is enough users that want to pay the premium, we get huge queuing delays and a horrible user experience. We can have minutes of wait time, and this is not real time at all. One solution that has been studied, and I also did it during my PhD 5 years ago, was the idea of sharding blockchains in order to get elastic scalability. What's the basic idea of sharding a blockchain? Well, when we have more users that want to use resources, then we would expect to also have more validators willing to give resources because they will get paid. So the more validators we have, we can start splitting the blockchain into smaller blockchains that validate subsets of the state. And as a result, we can keep doing that as we get more and more resources and always maintain an elastic scalable system. The good thing about sharding is that this requires pretty low cost per node. One node can have a minimum requirement for its resources, and many validators could show up if they match these requirements in order to validate. And of course, it does scale out. We can actually manage to get more and more load, of course, given that the load can be parallelized. However, sharding has some quite significant shortcomings. The first one is that it creates a fragmented state space. This means that we no longer are able to access the resources into multiple shards the same way as accessing the resource in a single shard. Instead, we need to run some expensive atomic commit protocols, and this will result in both higher latency for those transactions and higher cost because now we need to run transactions in multiple shards. Additionally, sharding is susceptible to adaptive adversaries because the adversary can target its power in a single shard, take it over, pollute the state in that one shard, and then through cross-chain transactions pollute the state of the whole system. And in general, it requires security drop. For example, if you look at sharding protocols like Omni ledgers, you're going to see that we assume adversaries that are lower than 1/3. In Omni ledger, for example, it's close to 1/4, in order to do this sampling process and still maintain security for every single shard. So in order to solve this elastic scalability in another way, our first step was really into looking on this consensus problem that basically until the last 2-3 years, it was really considered a single problem. We want to solve consensus and actually split it up into layers. And the layers we tried to do was get a layer below consensus, which we call mempool for legacy reasons, but it's really transaction dissemination, such that this mempool layer is going to send transactions without caring about ordering. And then the consensus can only handle the metadata of those transactions and order without having the full load. And on top of it, once you have consensus on transactions, we actually study an execution layer that takes as input an ordered set of transactions and simply executes them to get the final result. In order to study the first two layers, we present in Narwhal, which is a DAG-based mempool. And in a very short, the basic idea of Narwhal is that instead of having one machine that is running the full validation from sending transactions to running consensus to executing, instead we're going to open up the validator into multiple machines. And we're going to dedicate some of the machines for the transaction dissemination. These are the worker machines who basically collect transactions from the clients and send them as batches to the workers of the other validators. And then the primary now only gets a digest of the batches and then can communicate with the rest of the primaries in order to get a total order of those batch transactions. And because a digest is just a hash, you don't really have to optimize your consensus protocol to be high throughput in the sense of bytes, because it only handles metadata. And how it really works is that we have the Narwhal mempool in front of the clients. They send certificates to the consensus, meaning that these transaction batches are actually available. The majority of the nodes of the system have received them. And then the consensus sends order transactions to the execution, which would be the more interesting part later in the talk. And of course, there's a garbage collection between consensus and transaction dissemination in order to make sure that we don't run out of memory. Before we go into what we do at Pilotfish, we can also consider a simpler idea, which is sharding, but not sharding the full state from dissemination to ordering to execution, only sharding the execution. The basic idea here would be kind of similar to what layer 2s are doing, where you have the total ordering of transactions inside blocks that all of the executors C, and then you just shard the state for execution. This means that different shards are going to commit to the state updates of the transactions on each block. And every time there is a block, you're going to also see multiple state commitments of what transactions on different substates are changing. This actually is a bit better than the full sharding solution, in the sense that you no longer have the security problem, the security drop of the adversary that the classic sharding has, because execution post-ordering is a deterministic process. As a result, we don't need to run agreement on what the state should look like. We just need a majority threshold. It also does scale out, and it has a relatively low cost per execution node as well, in the sense that because we have a Narwhal-based mempool on the dissemination layer, we would want multiple workers on a validator, but the execution can happen with smaller machines. Unfortunately, this still suffers from a fragmented state space and is still susceptible to adaptive adversaries. So this is why we try to look a bit into how to get out of this fragmented state space problem. And the solution that we came up with is Pilotfish. Pilotfish is a distributed transaction execution layer or machine for lazy blockchains. Lazy blockchains are basically blockchains that order transactions without executing them. They defer execution for later on. And it follows kind of the same mindset as the Narwhal-based mempool, in the sense that we want to have multiple machines inside one validator in order to scale out without this being visible outside of the consensus subcomponent. So what we do is we say that the validator now is going to have sequencing workers and execution workers. The sequencing workers are the ones that hold transactions. So basically, they get the transactions as a committed sequence from the consensus or from checkpoints if they're re-executing. And basically, what they do is this sequence worker, each sequence worker owns a shard of transactions. And they just look at those transactions, check which objects or which accounts, depending on the programming model, the transactions are touching, and inform the execution workers that actually are the ones that own shards of the objects. They own shards of the state. So if we want to go through one example here, what happens is you get inside of sequence worker a committed sequence of transactions. This doesn't have to be sequential. You can run the same protocol concurrently for as many transactions as you like. So basically as many cores as the sequence worker has. The sequence worker is going to retrieve the transaction data from its storage and check inside every transaction what objects is this transaction touching. And then it's going to realize that some objects are in some different execution workers. It's going to determine which execution workers are the ones that are concerned from this transaction and really inform them. So it sends the transaction data to those execution workers who are going to continue with execution. So basically, if you want to see it in time, we have this transaction. It has a dedicated executor, in our case, execution worker 1. And the object that it's reading are on execution worker 2 and execution worker 3. So the sequence worker is going to inform the execution workers of the transaction. Each execution worker that has some objects to be read is going to wait until this transaction is basically the one that is being processed. And we know of the dependencies because the consensus has already given total ordering. So we know exactly which transactions depends on which transactions. So they're going to wait until it's time, and they're going to issue reads to the dedicated executor, who is going to execute the transaction, store it locally. Usually the dedicated executor is one of the ones that are writing, and inform anyone else whose state is also going to be changed from this transaction that the results are available so that they can update their local store and maybe issue further reads to transactions that are subsequent. As I said, why is this safe in a concurrent system? The basic idea of why this is safe, although this is happening in different validators and could happen in different ordering, right? They're not communicating on how they execute, but because the ordering of transaction is well defined, it comes in from the consensus layer. We already know exactly which transaction is going to wait for which other transaction, and we can block and wait for those to terminate. As a result, because there's this predefined ordering, we can actually do it safely. And if there is and this also acts as a back pressure basically between the sequencing workers, because the sequence workers are just processing transactions very, very fast. So at some point, the execution workers are going to say, please stop, we haven't proceeded with execution, and those two subsystems can work well in a pipeline. So this is a very high level of how the common path of Pilotfish works. On the negative side, it requires a bit more resources per validator because we're not just doing a trivial sharded scale out where we add more validators. We have a quorum, 100, 200, 300, 500 validators, and we require them to have worker machines. So it actually costs a bit more than in other sharding protocols, but because the only reason you are going to need more machines is because there is load, this is not actually cutting into the profits of the validators. They're going to only put more machines when there is more load and they can get more fees. And on the other benefits, it does scale out. It has a flat state space because it's only in one data center that we need to communicate between shards, so the latency is very low. And it also has a consistent threat model with the blockchain. We can actually have the same security guarantees as the consensus in the mempool layers. So we implemented Pilotfish, and here I have only two graphs. You can check more graphs in the paper. On the left-hand side, you see a latency throughput graph with 1, 2, 4, and 8 execution workers. And in this experiment, we're doing simple transfers, so just sending one coin from one account to another. As you see, with one execution worker, we can get a peak throughput of around 35,000 transactions per second, but the latency slowly increases when we get there because we actually are at the limit and there are some small queuing delays. As we increase the number of execution workers, we both get a scale out on the throughput side, where we go from 35 up to 60,000 transactions per second, but also because the resources are always available in the case of the execution workers, the latency doesn't really change much. We are still below 10 milliseconds of execution. And you can see on the right-hand side just the scale out graph. As you see, it's not linear in this case. And this is because simple transfers have no actual CPU overhead and no actual memory overhead. So it's really the only scheduling which is not perfect in our code base, and you see a bit of a flattening. If we go into an example where it's CPU bound, for example, in this case, we just had the validators compute some Fibonacci numbers in order to spend more time in the CPU, you see that the story changes and we can really linearly scale out. And this unlocks a lot of applications that might be CPU bound and are very costly currently in a blockchain environment. And our cryptography team is very happy that they can do cooler stuff without having to worry about extreme costs. Now, I have some more slides on crashing and recovery, but I can also pause for questions if people have questions.
I definitely have some questions, and I'm guessing the team does too, but don't want to interrupt if you have more slides. It'd be great to go through those too.
Okay, I can continue then. It's like not a lot of slides, probably less than 10 more minutes. So one of the major questions that we had when we were building Pilotfish is that it's cool and you can add more machines and all is nice and dandy. But what happens if servers start crashing? And you have one server, you can assume that it's going to be quite reliable. But if you scale to 10 execution worker machines and each one has like a 1% probability of failing in a month, then this piles up. You're going to have crashes all the time. One solution is, of course, ignore it and go and synchronize for the other validators outside of your validator. But this is very costly. So instead, we decided to start designing some fault-tolerant mechanisms inside the validator because we're going to have partial faults. It's not expected that the full validator with all the worker machines is going to crash. It might be that one execution worker crashes. So the first is just looking into what happens if a single execution worker crashes. The challenge there is that if the rest of the execution workers didn't realize right at the moment of the crash what happened, they can continue processing transactions and then forgetting of what they processed, like they're rewriting their local states. So when the crashed execution worker comes back alive, there is no state to help it catch up. That's why we're having a checkpoint product. It's not really a protocol, it's like a very simple checkpointing strategy where we're buffering messages. As we process transactions, we're going to just every 100 messages or every 1,000 messages, depending on how fast the protocol goes, just send a check between all the execution workers. I've reached around 100, I've reached around 200, I've reached around 300, etc. This let us know that if everyone, for example, has already reached around 300, then even if someone crashes, we don't need to remember of all the messages that we sent between 0 and 300 because they have locally gotten their state persisted to 300. So when they recover, they will start recovering from 300. And what we do is we make sure that we always have one stable checkpoint. A stable checkpoint is a checkpoint that every execution worker has reached. And we can have one or more pending checkpoints. In our case, we just have a single pending checkpoint. And the pending checkpoint really says that some have reached, but not every. And then we limit how many pending checkpoints are there. This means that if we have a maximum of one pending checkpoint in our case, and some execution worker has reached around 500, it's going to stop. And this is so that we create some back pressure and we allow the rest of the execution workers to catch up and the protocol can move forward in not lockstep, but some synchronized steps so that we make sure they don't run far ahead. This is on the checkpointing strategy. But then it can happen that the failures are too many and you have all the time an execution worker recovering, and we also don't like that. Again, one way that we would recover is go to other validators if we have actually managed to run far away from the buffered messages. But we also saw that we can use some simple replication protocols without even running full consensus. So what we do is, let's see. So the basic insights of why is that inside the cluster, inside our validators, we don't have to run BFT protocols. We don't need any cryptography. We don't need to have any equivocation protection. We're in a single data center. Additionally, as I already mentioned for other design choices, the sequence is already defined and persistent. And finally, we don't need to make sure that our replication strategies are very robust. It's good that they don't fail, but if they fail once a year, it's okay. We can just actually go and run the synchronization protocol with the other validators. So having all this into mind, we just created a very simple replication protocol where we just create different clusters of the full set of execution workers. In our case here, we have 2 execution workers. And then we just create a second cluster with execution workers. They run in parallel. They don't really communicate much other than checking with each other how far ahead they've been with the buffering messages. But when the one side of the cluster, the one execution workers crashes, we don't need to pause the whole cluster. Instead, the rest of the execution workers can just go and subscribe to the peer node of the other cluster for the same shard and run ahead and keep executing while that one node is recovering. And this means that we can also make sure that they synchronize and update their buffer messages so that no one really stays far behind. So to conclude, Pilotfish is designed to really run over something like Pulsar, something like a Narwhal-based blockchain that is already elastically scalable on the dissemination and consensus layer. And together with Pilotfish, we can get an end-to-end elastic distributed ledger. Because we don't use batching, every transaction is really streamed through after consensus, the latencies we see are around 20 to 50 milliseconds, which is quite negligible compared to the 700 to 900 milliseconds that we have on the rest of the protocol. And if you co-design something like Pilotfish, knowing that you're going to run it with a blockchain, that means it already has BFT replication, it already gets a total ordering of transactions and determines out of that, you can get very lightweight recovery protocols. So yeah, thank you very much. Can you hear me?
Oh yeah, thanks so much. Sorry for that. Yeah, I think there's a couple of questions, so I'll leave it to them if you have time for Q&A.
Yeah.
Awesome.
Please go on, because I only have my presentation and I don't see hands or anything.
Okay, cool. Patrick, do you want to go first?
I clicked the wrong button when I was trying to clap, so you should go to Steven. I think he's first, yeah.
I did a little fake like clap with my hands, but I actually did raise my hand. So I was like, so I guess the kind of overall design here, right, is like the observation that you have a high throughput chain, but if you're in periods of low activity, then there's no reason to actually like kind of maintain all that additional hardware, right? But like, I wonder if something that we've kind of observed is that if your fees get low enough, then essentially the activity will show up, because, you know, say you have some DEX on chain, right? Like the kind of the margins, or like the ARB opportunities end up being a function of the TX fees. And, you know, if your TX fees are decreasing based on low usage, then essentially like that usage will end up coming up to take those opportunities. So is this you know, like how does this kind of interact with the dynamic fees is, I guess, my concrete question.
So maybe to start a bit on your observation first, it's not only that it's like, oh, you need to have additional hardware in case the spike shows up. Is that if you don't have the elastic scalability at the execution layer, then you need to provision a machine with a lot of hardware. And you can't just bring a second machine, right? So here, the other part is that you can have a weak machine at the beginning when you don't have load, and then just bring a second or a third or a fourth machine without having to go and buy a 16-core 500G RAM machine when the load shows up. So it is also the fact that you can provision your validators lower later on. Now for the dynamic fees, really what we believe is that a blockchain is really kind of a public good for like executing reliably smart contracts. And as a result, as long as you can make profits as a validator, you don't need to be in the case of running auctions and making it a scarce resource. As long as you can always make profits because you can actually scale up and down the machines that you're running, then there should be a market, right? And if you have a fair market, more and more users are going to show up. So your margins are going to keep increasing. You're going to keep making more money if you have some marginal per transaction profit.
So essentially, you kind of view like the fees that are being paid by users as a market paying for like the validator hardware, and then you would expect over time those numbers to be approximately equal with some profit margin for validators.
Yeah, exactly. Like there's demand and supply, right? And as long as you can always satisfy it, you're like, if I'm losing, I'm going to get out of the game. But I don't need to make it a scarce resource like it's now on Ethereum, right? This is actually driving away users who are like, why should I pay $3 for buying a coffee, right? I will just use my credit card.
At the end of the day, it's like controlled by validators, right? Because like the actual like hardware.
Sure,
kind of
sure. It's controlled by
off-chain.
validators. And at SUI, for example, we have like every epoch, there is a voting phase where we see what the supermajority of validators want to charge per unit of operation. So of course, they could, in principle, run I don't know, like, I don't know how to say it now. It can be a closed system where they just do whatever they want on the fees. But then maybe the users are going to go and stake with other validators. Like, I'm not 100% sure, but we don't really assume a two-third collusion here. Cool.
Patrick, I think you can just shout out.
Yeah, this time I did mean to raise my hand. Thanks for the talk. Appreciate it. I think a less thought I feel like has gone into this, like expanding the capacity of each particular validator rather than like kind of assuming that the constraint is a single machine. So I think that's interesting. The biggest question I kind of had was, I think the paper at least talks a bit about how state is kind of separated between different executors to, because you can't have potentially you may not like be able to keep everything up to date across all parts of the machine during a processing block, or maybe for efficiency reasons you may want to split it up. Have you thought much about like potentially like adversarial workloads that like purposely reference like state across like 2 different execution machines or 3 different execution machines, such that like each transaction execution requires touching like all participants or something like that, such that the global output of like the workload would be far lower than like a single machine ever could be, because of all like the network interaction or like all the locking and like everything that would be required to make that happen?
Yeah, so I think that this is a common problem for all sharding designs, that you can have like a very adversarial workload that makes sure to touch everything. You could try to rebalance your state slowly so that if you see this as a legitimate pattern, then you move some of the keys to be more collocated. But in general, I guess the other way would be really to start adding in the fees, the cost. I don't think that someone is going to start doing it. Also, we're in one data center, right? So it is very marginal, the cost of communicating between machines. Currently, we do run through TCP, so it's a bit of a cost, but you could imagine having RDMA, and then it really is, it's very marginal to almost non-visible.
And your point about fees there is basically that if you were to do it, you would just charge more if like the keys were on separate.
Yes, I don't love
basically.
it. It kind of happens already in like the classic sharding in my first slides. It kind of happens already because you have to execute in every single blockchain.
Yep.
In our case, it doesn't. You could. I don't love it. I would want to see that it's a problem, and that even if I actually have like shared memory RDMA communication between the validators, it still costs more.
Yeah, I think at least from a practical perspective, some of the data centers now are like, at least AWS, let you like share the same. Have you seen this? Like share the same EBS volume across up to 16 machines. So like you can have like your like basically as quick as you would if it was just hooked up to your machine, but then like give everybody uniform access to like the same IoT block express.
Exactly.
Yeah.
So like there are ways around it that will make it very, like, not a very powerful attack unless like you really want to kill the chain. Not kill the chain. Like I don't think it will be a very powerful attack.
One question that I had, I think it was on maybe the 5th or 6th slide or so. But when you're talking about parallelizing access in the graph that you showed, you get sort of the input from the sequence worker, and then it tells you what to read, and then the execution worker already knows in advance what to read so that it can decide how to parallelize the operations. Is that assuming that the transactions specify either the state keys they're going to touch at all, their read-write access, or is it assuming that it's generated by consensus and then sent to the rest of, or like by the block builder or something? Where is that actually generated and specified?
Yes. So in our programming model in Move, it's actually mostly specified what you're going to read and write. You can have some dynamic accesses, but they follow a hierarchical path, which means that there is like a parent object, which is the table, and then you can dynamically access parts of the table. So there is some trade-offs there on how much data is going to be moved around, and you can see more of the paper. But in general, this kind of system that scales out this way would need the knowledge of read and write sets. As you said, you could try to do it in a pre-execution way, actually like try to compute on the fly something. You can try to abort if you're using multi-value concurrency control on the back. But yeah, in general, it is not suitable for a system that has no idea of the access patterns.
I see. Okay, that makes sense. And so the move VM itself sort of provides that hint on this hierarchical access of what subkeys it's going to end up touching. Does it? But I'm guessing that it doesn't prefetch all of those sort of subkeys. Does it sort of say exactly what it's going to touch, or what? Can you tell me a little bit more about that?
So basically what happens is that you define that you're going to touch this table. So we make sure that this table is locked for this transaction. And then on the fly, you can keep shipping more and more data. So there's a back and forth between execution workers. Hopefully, you're not going to touch everything, and then it can become costly. But this also, back to the previous question, if you do have a shared memory, it becomes, again, not a problem. You can actually just go and bring whatever you like directly.
I see. That makes sense. So you're locking the higher level objects. You don't need to pre-cache everything. Yeah, it makes sense.
Yeah.
Another question that I had is, since you're optimizing for elastic scalability, where you're going to spin up additional machines in order to meet demand, would you say that you're targeting people running nodes inside of a cloud use case, as opposed to like, well, I'm running a home node on my Raspberry Pi 4, and I want to be able to go to Amazon and ship me like 10 additional Raspberry Pi 4s or something along those lines? Is that sort of part of your model that you're planning to run these in data centers with certain primitives that are there? Or how do you think about that?
Yeah, so currently we're considering a bit more of a professional validator that could do that. Other than that, you would need a bit more provisioning time, so it's not fully elastic.
Cool. Yeah, that makes sense. Another question that I had, and this is not super specific, so just let me know if it's not specific enough to realistically give an answer, but the fees in this model is very interesting. I know that Steven sort of alluded to it and you talked about it a bit already, but could you just give the high level of how you expect fees to go in like the ideal world? How would the fees sort of react to increasing demand? What does that sort of step function look like? Because it could be there's an increased demand for more throughput, more state access, and then we spin up additional hardware. What exactly does that look like?
So maybe there is two questions here, because like there is fees in general for resources, and there is fees for a specific resource. So which means that like if there is contention on one key, there's contention on one key, and elastic scalability cannot save that, right? So what we envision is really having a market that when there is congestion in a single key, it actually creates an auction. But in general, all the rest of the resources, assuming you have enough hardware, are really on the marginal cost of the validator. Does it make sense?
Cool. Yeah, that makes sense.
One, not to keep harping on fees, I just find it fascinating. So this is kind of viewing stuff as like kind of like one-off. Like this feels very tailored to execution costs, but like a big thing with blockchains is kind of like the active state size. Like if you scale up your system, right, and then it becomes a lot cheaper to say like store data. You can't really like scale that storage down that easily after that point, can you? Like do you guys like impose a like state rent mechanism to do that, or like is storing something like a one-time fee? Like
so
how does that
so this is general, like it's not about Pilotfish, but Sui has a storage what is it called, a storage fund, where when you create transactions and the transactions take some state, then some of your fees go in the storage fund, which is then basically used to create more and more value because it's just, SUI, you can stake it, right? And when you delete the state, you can actually get a storage rebate.
Yeah, I guess I'm just mainly interested. So I think that answers my question, but yeah, I'm just mainly interested because like with Pilotfish, right? Like if you expand up, say like your validators like, yeah, we'll let you store stuff and like take profits, right? Then all of a sudden they're like, okay, now like it's actually becoming too expensive for us to store this stuff. We're gonna like leave the validator set. And then all of a sudden you have people that need to kind of maintain that state. But if you're doing like a state rent,
so because the fees go in a storage fund, they don't go to the validator, then this is going to generate fees, let's say. I don't know how to say it, like more fees for the future validators that store it.
Makes sense. Cool.
Cool. Yeah, that's all the questions I had. Does anybody else have any questions? Awesome. All right. Thank you so much for coming, Lefteris. This was a really awesome presentation. I really appreciate it.
Thank you very much for having me.